This video is going to focus on the different types of mixtures, ways to separate mixtures, and then eventually elements and compounds. It's another section that is very vocab heavy. There's no math here, so you really need to focus on memorizing the vocab and knowing different examples. So a mixture is a physical blend of two or more things. All right, the key word is here, it's a physical blending. All right, meaning you can get it apart essentially. It's not a chemical change. You're not getting a new substance. Therefore, it can be reversed. So there's two types of mixtures, homogeneous and heterogeneous mixtures. Homogeneous are going to be uniform throughout. Okay, so we say that homogeneous mixtures have this uniform composition throughout, and a heterogeneous mixture is not uniform throughout. So the easiest way to think of this before we get into some examples here, for a homogeneous mixture, if you took multiple spoonfuls of a specific substance and every spoonful was exactly the same, that would be a homogeneous mixture. Okay, if you can't identify the individual components in your sample, if you took multiple spoonfuls, then that's going to be homogeneous. All right, heterogeneous would be where if you took multiple spoonfuls of the same substance and you got kind of a different composition in each of those spoonfuls. Basically, you could kind of pick out the individual parts. So let's look at some examples here. If we did Mountain Dew as an example, right? Would this be homogeneous or heterogeneous? Think about it. If you took multiple spoonfuls of Mountain Dew, would the spoonfuls be the same? Yes. So Mountain Dew is going to be homogeneous. Okay. You wouldn't see like the different amounts of, say, the sugar or the carbon dioxide in there. It would just, every spoonful would be the same. But if we did this for chicken noodle soup, if you took multiple spoonfuls of chicken noodle soup, would every spoonful be the same? No, because chicken noodle soup is a heterogeneous mixture. It's not uniform throughout. Maybe one spoonful has all noodles and some broth. Maybe the next spoonful has, a carrot and a piece of chicken, but no noodles. So every spoonful would be different. And if you had some M&Ms here, specifically if you focus on the color of the M&Ms, if you took multiple spoonfuls of the M&M, they would be heterogeneous because they wouldn't be the exact same color ratio every time. So definitely know the difference between homogeneous and heterogeneous mixtures here. But mixtures are physical blends of two or more things. They are not a chemical change. Some more examples here to practice homogeneous and heterogeneous mixtures. If we had chocolate pudding, would that be homogeneous or heterogeneous? That would be homogeneous. Multiple spoonfuls, every spoonful would be exactly the same. If you had salad dressing here specifically, like oil-based salad dressings, you would expect that to be heterogeneous. It's not going to mix so well. If you took some salt and put it in water, gave it a stir, now you have salt water, that would be homogeneous. It's going to be evenly distributed throughout here as long as you don't have a pile of salt on the bottom. A DQ Blizzard, you would expect that to be heterogeneous. Maybe one spoonful has all ice cream. The next spoonful has a nice chunk of, say, candy in it, depending on what kind of Blizzard you got. So every spoonful would be different. So heterogeneous. And vinegar here would be homogeneous. So definitely know the difference between the two with examples. Solutions now are a special form of a mixture. Solutions are homogeneous mixtures, so they are evenly distributed throughout, but one substance is dissolved in another. So realize here, solutions are mixtures, so they're physical blends. It's just that they are a specific type of homogeneous mixture, so totally uniform throughout. So there's a lot of vocab that goes with this. The solute is the substance that is dissolved in a solution, and the solvent is the substance doing the dissolving. All right, so a solution has one substance dissolved in another. The solute is dissolved by the solvent here. So if we look at some examples, if we look at this for lemonade, lemonade is going to be a homogeneous mixture here. It's a solution. So what would be the solute in lemonade? There's actually a bunch of different ones you could go with, but the big one here in lemonade would probably be sugar. Maybe depending on how you're making it, the mix could be your solute, and then the solvent would be the water. that would be dissolving the sugar here. So your solute is a substance that is dissolved, and then the solvent does the dissolving. So what if we had some soda here? What would be the solute in soda? There's actually a few of them. The big one I'm going to go with here is going to be sugar. You could say caffeine. You could maybe say the syrup. And then what would be the main solvent here in soda? Would be water. Okay, the water is going to dissolve those different substances. And if we did this for ocean water, right, the solute in ocean water would be the salt. So you have the salt is dissolved, and what's doing the dissolving? The water. All right, you might have heard water called the universal solvent. It can dissolve many things, not everything, but many things. There are some things here, as you see here at the bottom, that are insoluble in water that do not dissolve. So certain substances do not dissolve in water. Sand would not dissolve in water. It's going to be insoluble. But something like, sugar or salt, they are soluble in water. They do dissolve. So you should definitely know these vocab terms here. Definitely know what a solution is and, different examples. What are some different things here that affect the solubility rate? We're not talking about things that, make something go from uh, insoluble to soluble. No, if something is insoluble, it's not going to dissolve. What we're talking about here is if you have something that does dissolve, it is soluble. What are some things we can do to maybe speed that up? All right. So the big one here is temperature. If you just increase the temperature of a substance, you increase the rate that something will dissolve. The easiest example to think about with these things is like your cup of coffee. All right. A hot cup of coffee is going to dissolve the sugar much faster than a cold cup of coffee or an iced cup of coffee. If you typically get an iced coffee and you add sugar to it, the first sip is usually a nice amount of sugar. All right. So the higher the temperature, the faster that sugar will dissolve. And then again, you can think about your coffee. Stirring it makes the sugar dissolve faster. All right. So we're talking about here things that could increase the rate of dissolving. Just stir it up and it will dissolve the sugar much faster. Concentration here is kind of reversed. All right. The more you add, the less soluble it will become. All right. So concentration is kind of an opposite one here. Right. If you add too much sugar, it's not going to dissolve that fast. Versus if you have a big cup of coffee and you only add a tiny little bit of sugar, that sugar is going to dissolve much faster. And then the greater surface area a solute has, the more quickly it will dissolve. So this is why, we add crushed sugar to our coffee versus sugar cubes. Sugar cubes have a specific amount of sugar in them, but when the coffee is attacking the sugar, it's really only attacking from the six sides. It can't get to all the molecules of the sugar at once. If the sugar is crushed up and you throw it in, the coffee is literally attacking all those sugar molecules at once, so it dissolves much faster. So these are different things that can maybe speed up how something dissolves. And you could see here the easiest example to think about is your cup of coffee with your sugar. Because mixtures are physical blends, that means they can be separated here. So you can use different physical properties to separate a mixture. There's no chemical change taking place when a mixture is formed, so you can separate them. So here's some different methods you can use for separating a mixture. They're not the only ones, but they're definitely some ideas here. The first one is decanting. So that would be the actual way to do it. If you have two substances that have a different density, then you could just pour one layer off, leaving the other layer behind. So the physical property here that you're using to separate the substance is density, right? But the method is decanting or pouring it off. So each of these methods have a physical property you can use to separate them. So filtration, for example, is when you're separating a solid from a liquid. And the basic gist is that you have one of the substances that is not soluble in the liquid. So the liquid goes through and the solid gets kind of trapped behind. You could use a magnet. The physical property here of iron is that it's magnetic. So you could use a magnet to kind of pull out iron in a mixture. Something here called chromatography could be used to separate colors. You can see here in the picture, if you put a mixture of colors down here on this starting line and then allowed the solvent to run up the paper, the different colors in the mixture can separate out. So this is something pretty cool. You can do something with this with leaf pigment colors. You could do this with different colored candies or markers. So there's some interesting things you can do with chromatography, but it's a way to separate different colors. And then another way to separate a mixture is through distillation. This uses a difference in boiling points of two substances in order to separate them out. So this is a little bit more complex, and I have a picture of this to explain this on the next slide. So these are just different ways to separate a mixture. There are other ways too, but the key is because mixtures are physical blends, they can be separated. So here is a distillation apparatus. Basically, how this would work is if you took a mixture, so in this case, it's tap water. Whether you realize or not, there are other things dissolved in tap water. There's fluoride in there. There could be, who knows, other contaminants like lead. So what you would do here is you would heat this up. All right. You know that pure water would boil at 100 degrees Celsius. So you basically start heating this up and you monitor the temperature here. And this is all sealed. So what happens is this heats up and starts to boil. Once it gets to 100 degrees, it starts to turn to steam. All right. But when it gets here to the top, that steam has nowhere to go because it's blocked. So it heads down this little side arm into this condenser tube. All right. This condenser tube is kind of like a tube within a tube. So the steam is kind of in the inner part of the tube. And then in a separate kind of outer part of the tube, you're running cold water through it. So this hot steam is coming in contact with this cold water, but they're not mixing because they're in separate tubes. So you're pumping this cold water in. Well, as the hot steam moves down the tube and you have this cold water surrounding it, the steam will recondense back into pure liquid water and that will come out the other end. So that would be your distilled water. It's pure water, right? So this is a basic distillation apparatus. As long as you're monitoring this temperature, the other stuff that was in the water would not boil out at 100 degrees Celsius and it would stay behind and you'd be left with pure water coming out. Okay, so as the pure steam here travels up this tube and then it heads down the condenser and it's cooled down by the water on the outside of it, it turns back into pure water. And as long as you monitor that temperature, the other stuff would be left behind in this flask. All right, so this is a way that they can make moonshine. If you've ever seen the show Moonshiners, they basically don't use this exact apparatus in terms of the glassware, but the idea is kind of the same. You have the alcohol that's kind of turned to steam. It goes through a series of, coils here where it's recooled back down into pure liquid. All right, so it's the same idea, but this is another way to separate a mixture through distillation and differences in boiling points. A few more terms here. I told you this section is very vocab heavy. A pure substance has a composition that does not vary. So a mixture cannot be a pure substance because when a mixture is formed, you could add a little bit of this, a little bit of that. Every time it could be completely different. So mixtures are not pure substances. Pure substances have a composition that does not vary. All right. Elements and compounds are pure substances because their composition does not vary. An element is the simplest form of matter that has a specific set of properties here. So any of the elements on the periodic table are examples: hydrogen, oxygen, gold, chlorine, zinc, so on and so forth. All right, so you can see here's a picture of chlorine gas. It's this yellowish gas. It's a simple form of matter. It's a pure substance. The composition does not vary. Compounds, on the other hand, contain two or more elements chemically combined in a fixed proportion. All right. The key here is that compounds are chemically combined. Compounds are different from mixtures because they are chemically combined. It's not like a mixture. A mixture is a physical blend that you can separate. A compound you cannot get apart unless you undergo a chemical change. Another difference here between mixtures and compounds is that compounds have a fixed proportion. What we mean by that is that they have a specific ratio. Because they're a pure substance, their composition does not vary. All right, so think about water, H2O. You have two hydrogens for every one oxygen. You must have that ratio in order to be water. All right, It's not like a mixture where you add a little bit of this, a little bit of that. You must have 2 hydrogen for 1 oxygen in order to be water. So compounds are chemically combined in a specific ratio, a fixed proportion. Carbon dioxide is another example of a compound, CO2, 1 carbon for every 2 oxygen. You might have heard of, glucose C6H12O6. There's a specific amount of each of them, right? So you definitely need to know the difference between mixtures and compounds with examples. Elements and compounds are pure substances. Their composition does not vary. So we're not going to spend a lot of time on this, but this is just a different way here that you can look at this and classify matter. You can follow the flow chart here and look at, the difference between mixtures and, elements and compounds. The last thing I want to talk about in this video are chemical symbols. So every element has a 1 or 2 letter symbol. So if you look on the periodic table, every element has a 1 or 2 letter symbol. The first letter is always capitalized, and if the second letter is there, it's going to be lowercase. You have to get used to writing it that way. Someone like myself who writes in all capitals, I have to be very careful when I'm doing element symbols because the second letter, if it's there, is always lowercase. Some of these are literally the first letter or the first 2 letters of the name. So they're pretty easy. Like HE is helium, first 2 letters. H is hydrogen, first letter. Bromine is Br. So some of them are pretty easy. You might know some of them, but then other ones come from the Latin name. So the letter or the 2 letters have nothing to do with the name. So for example, K, well, that's potassium. Notice that's not even in the word potassium because it's coming from the Latin name. Na is sodium. Ag is silver. So you definitely got to be careful with some of these. There are specific element symbols that you need to know. So we will talk about this in class, and you have to know specific ones because you got to be familiar with them and know them off the top of your head, so you don't have to look them up every single time.